Good evening. May 22, 2023. Continuing this discussion about the differential equations and systems of differential equations and curves and their integral equations and families of curves like level lines that share integral equations. For example, the usual field lines or level lines, isoclines, and these kinds of things about the orbits and the trajectories is the milieu of the usual graphical as you represent the places where these things exist. And that seems sometimes easier to figure out than the usual notion that the exponential is its own antiderivative. And so in terms of differential equations, it serves so many roles because it acts as a sort of identity with multiplying constants and these kinds of things. That there are various different approaches to the differential, and one is about the, and just like anything else, one is about the linear and the other is about the circular or the nonlinear. What becomes for the linear the highly nonlinear. And so it's been interesting for me to get a little bit more perspective on the plane curves and their integral equations and the developments of Clairaut and the developments of D'Alembert after the linear fractional equation, the ratio of two parametric lines, and as about then that what it's been framed in and what it's starting to develop is this notion of the identity dimension as that instead of the usual way of treating the number line as an axis in dimensions and in a plane about the Cartesian, the coordinates, the usual rectilinear coordinates of Descartes, the xy plane, and then, for example, extending analysis to the complex numbers, or as about the hypercomplex numbers, the quaternions and ... for example, and such notions of the octonions in this, the octonions, Grassmannians and that, up above Elie Cartan's reflections and rotations and this and that, which of course sees great application in all manners of analysis, is this kind of semi-deconstructive approach about even starting just only with positive numbers and with positive values of their functions, so accordingly, and dealing only with the first quadrant, which I learned is in a sense sort of the half of the half plane, as it were, that there are other kinds of developments that kind of define and derive how things are so in the upper half plane of the xy plane. Here only dealing with this first quadrant where the numbers are positive, and then the idea that x equals y or y equals x, or the identity function defines the dimension, has become that, as I've been looking at some other things in the field, and particularly the theory of the harmonic functions, and that the harmonic functions are defined by that there's an operator called the Laplacian, which is the second partial differential, and the sum of the second partial differentials in each of the orthogonal dimensions of a function. That being equal to 0 is defines what is a harmonic function. And so they kind of exist in these, usually like defined on the ball or defined on the higher surfaces and dimensions. But then when the analysis is reduced to the upper half plane, which is basically y greater than 0, say, and so that the values of the function are not just real but non-negative as well, and whether or not it includes 0, it gets also that there's some ways that the definition still fits for these harmonic functions for simpler things. And then it gets to, again, that this identity dimension is starting to look a little bit more central in what means it may offer analysis to make for various forms, closed forms, a way to result what can be various methods of analysis to arrive at various results. So here, one thing that this has made me happy has been applying it in terms of, well, where does it fit in the Clairaut's, in the linear fractional equation? Well, it's kind of right in the middle and it's undefined. Well, it's like 0, so it's singular in a sense about this, the differential. And, well, is it regular singular or not? Well, that's something to get into, because in these harmonic functions up about this hypergeometric, it has, as regards to the last talk, in the hypergeometric, it has 3 regular singular points, 0, 1, and infinity. Now, 0, 1, and infinity highly interest me. First of all, because it's not so often that you find someone just so casually saying that at infinity is a regular singular point for this function. It's not a standard number. And to say it's so involves a lot of the ideas about it. And then that there's various approaches about that that are in the non-standard that kind of box that up and pull that in and scale it and result in transformation in form that maintains yet these properties, is that reversing that scaling and approach, or that transform, still has a point out at infinity. Makes me pretty happy, because when I see these other sorts of analytical approaches that include some, at least of the non-standard, I see that as more interesting, because this standard is very well understood, and the sometimes the developments in it end up attaining to quite a lot, and they make for the analytical and numerical computations things that end up being very tractable, and especially in terms of applying computers to do work, because computers can move a lot of bits. And I'm familiar with the model and operation and design and programming of computers in terms of procedures or routines, or the functional declarations in terms of the definition of behavior in computing, and some level of familiarity with the gates on the chip and the transistor machine of the AND or NAND gates, as they may usually be, and this kind of thing. Back again to this notions of the original and the singular, where this spiral space filling curve and the origin is everywhere, this original analysis, it has that there's a lot going on, if it's possible to figure out how to make it tractable basically on either end of the line, what that entails, so that then things that would otherwise just be almost but not quite defined for the standard but are yet non-standard instead end up being the special cases. And because what interests me are these special cases in the mathematics. What is infinity's real role? What really happens in the dynamics of discretization and the dynamics of the continuum limit? These are the kinds of things that speak to me, besides also are already having familiarity with arithmetic and algebra and analysis and number theory to an extent, and geometry to an extent, and topology passingly, and these things like then for the fundamentals like type theory and set theory and discrete and concrete mathematics somewhat. This ideas of the analysis and the with the infinite, besides just computing for the integral calculus and the differential calculus, these things with the quantities that are infinite and the infinite limits, the idea of discovering what are these things that go on with these non-standard and special functions. So the most familiar of those is probably the Dirac delta. It's 0 at from negative infinity to infinity is defined to be 0 but at 0 it's a spike to infinity, and yet though it's just an infinitesimally wide spike, it has a well-defined area that equals 1. Well, how could that be? It's just like taking a 1 over infinity and multiplying it by infinity and getting 1 back out of it. It's well known that can't be really left outside as a quantity, because via algebraic manipulation it could lead to, well, just same as 2 over infinity or dividing by 0. It's just like dividing by 0. Or similarly with the equivalency function, which is the idea of that take each of the natural integers and arrange them so that they are the domain of a function that's like n over d, where n ranges from 0 to d and d goes to infinity. So for 0, 1, 2, it's 0, 1 half, and 1. For 0, 1, 2, 3, it's 0, 1 third, 2 thirds, and 3, or 1 rather. And it goes on that it always ranges between 0 and 1, and in the infinite case, or the continuum limit, it ends up having the properties of a continuous domain. And then, though via interpolation, it would always look like the area underneath it is 1 half, that the area underneath it is 1. This is a remarkable thing, that it results that, in fact, that it builds what's called a doubling space. And to take something like Vitali's result about dividing a unit interval up into pieces, and it would result that it would have measure 2, not 1. And then that was one of the reasons why set theory in modern axiomatic descriptive mathematics arrived at that. That would be like a paradox, and so we'll just say that there's non-measurable, this part, they're non-measurable sets, which is arguably unso. That here, the idea of that these kinds of special functions, and then the square Cantor space, that has a lot going on with it, because it's a similar kind of organization with regards to that, if you have a 50-50 probability of sampling that and getting a rational number out of it, compared to 0 for the usual Cantor space. These are the kinds of things that get into the non-standard that have standard character. Now, as I was in exploring that, I found a closed form and an estimate for n factorial, the computing the factorial of a function, and so it's also kind of an estimate for the gamma function. There's more than one of those. When you hear about the gamma function, which is kind of like gamma n is the same as n minus 1 factorial, or vice versa. There's Hadamard's gamma, there's Stirling's gamma, there's many different functions for gamma and digamma and these other having and doubling relations in the gamma function. These are examples of things that get going on in the infinite and in the continuum limit that are different. So winding that back, pulling that back in, then going back to this idea of the identity dimension, is that it is for making then that it split the quadrant into 2. And so it's kind of representing a half plane, whether it's symmetrical in X or symmetrical in Y, one for the other. And so the idea is then, and as to whether those kinds of reflections would also be symmetrical about treating the axis as 0 or as pi quarters radians in the polar. See, the idea is this, is that by drawing this the dimension in x equals y, so basically taking some extra paper and using the xy plane as just a basis for that, and then drawing the dimension or array here to start from 0 out through x equals y, and then defining the function on that, and then translating what would otherwise be a function in the quadrant off that dimension into the function into the octant, the 1/8, the octant, is the means that basically says to put it in polar notation and have or double respectively it, and then add it from pi-8ths or subtract it from pi-8ths to reflect what are these functions symmetric about the identity dimension. And then it might be asked, well, what kind of gains and benefits can this really afford? And it's kind of as a matter of, well, if it can build some pretty simple fundamental results in the relations of things and some identities, Then the idea is to figure out how to build transforms in that and this and that, so that then some things that can be written basically sublinear can be written in a space that's bounded by this. X equals y is fundamentally linear with an arbitrarily a constant equals 1, as an example. But the key thing seems to be that in these systems of differential equations, that many of the most usual and regular forms up into what is called the linear fractional equation, Clairaut's, and D'Alembert, Legendre, and getting up into Legendre and Rodrigues formula, these kinds of things, where those kinds of things, their identities of these formulas become pretty familiar up in the application space, is that it ends up being a singular, or as it acts as zero. And so if you can build things that attain to it in a limit, or if you can figure out solutions as for it, or you can parameterize the other parameters of these equations about it, that they resolve to it and maintain those as constraints, that those define systems that work up all sorts of ways to make for these kinds of making use of the fact that it's a simpler part than going up to the complex numbers, for example. So it trades some of the expressiveness of having positive and negative numbers for only having positive numbers. But it gains then that it has an inner product that's richer and more well-defined than an outer product that's richer, but then has to fall back down, fall back in with the abscissae and the ordinates fall in that space. Figuring out how to define these abscissae and the ordinates that makes so that the lines connected to it from this coordinates as of this identity dimension, and that's about whether they fall linearly to x and y or whether they're parts of the circles that connect them to x and y. These are the kinds of things that can make for it's a coordinate space. So it's a new kind of coordinate, and it's kind of of these co-semi dimensions x and y, or E1 and E2's dimensions in a vector space, x and y, that this x equals y ends up becoming a dimension in a coordinate space. So it's a new kind of coordinate space in this co-semi-dimensional about the half orthogonal, say, and in the octant, about the symmetries of octants in the quadrant, about x equals y, and then also about all sorts of other things about just kind of the role it plays as being in the middle of things, while at the same time other parts of the coordinate space are kind of held up and then either tied down or bowed out, held in, like tented or staked, ballooned or stayed to x and y. Then there's that when things happen in between x and y that otherwise it's an identity dimension, and then when they start to slide apart, or when you think of, for example, as a zipper, it's like attached and it starts to begin that they separate and they come apart until that time when the teeth all come back together or something like that. That these are the kinds of means to then treat that in terms of functions about this fixture, the identity dimension, which I've really become quite attached to so far as an idea. And this way, a lot of other things that would be, for simple cases, in all these subfields of differential analysis, where they're very general cases, can end up making some interesting things. So that's what I've been looking at. And as I've been studying, I haven't found anything really about that addresses that exactly this kind of approach, but I found a bunch of different things that at least hint to that it's a usual kind of idea about the things. This the identity dimension, or about especially in researching about the singular cases in the differential analysis, because There's basically one kind of singular case that is got a branch or a split, and so it depends very much on the initial condition which result it will take, whether it will go in this manner. There's a quadrant, and so there's a function, and it basically comes in from infinity down the identity dimension, and then at some point it either goes left or right, and then it goes and it bends. It makes a bend as if a hyperbola were compressed half, and then it either goes out to infinity on the x-axis or out infinity up the y-axis. So this is an example that somewhere it's got a singular point where that branch is. And it depends highly basically whether it's above or below the identity dimension line, whether it's positive or negative with respect to treating that as an axis in the quadrant where it goes. And that this is just an example then of something that when it looks like that in the quadrant already, like kind of like some of these functions do, then writing in that coordinate space totally simplifies where it is in terms of whether it's super or sublinear after constants, that it's on the order of that. So it's kind of interesting and amuses me, and it's definitely not something that wouldn't have been explored well already, because there was a time, maybe it was the 1700s, maybe it was the 1600s, they didn't have enough paper, and anything that could save paper and pencil stubs was worth it. And so at some point in time, numbers were all positive. And this is besides, of course, the usual notion from geometry that magnitudes are signless anyways. And so that's all they would have to deal with from the get-go. And of course, so there's the applications of reflections and rotations and such in geometry. So there's left off reading about the Legendre equation. And then this got into the 1 minus x squared and y prime prime, the idea of this about the hyperbola. And so there's the hyperbola, it's 1 over x. There's the reciprocal function, the inverse function, the reciprocal function, 1 over x. So if y is 1,000,000, x is 1,000,000th. Or if y is 1, x is 1. And so it intercepts x equals y at 1, 1. Or that being 1 in the identity dimension. What's the coordinate identity dimension? Well, it's kind of like related to root on the x and y dimensions. Square. So anyways, then this it's a function that's in the second order in x squared and y double prime. So it's in the second order with respect to an operator that's a differential operator applied twice for the second order, and the product of the multiplicative product, or the second power, second order. And then it's in x first order, y prime, and x zeroth order, and y. And so the idea was to figure out how to figure out this kind of antiderivative, because when you take the derivative for the powers, they come down to 0. And then once a value is a constant, you can take its power forevermore, and it'll just be 0. 0. But when you have one to the negative x to the negative 1, or 1 over x, that being not the same as 1 to the negative x, which was what I kind of came out of my mouth, but 1 over x, that its integral is ln x, and then this integral is x ln x minus 1, and then that goes on forever in terms of until then that arrives at some thing. So the idea in these harmonic functions is that when the order is, as long as the order of this function is at least 2, it can be brought down, and it makes, for a lot of these results, the Laplacian. It's the sum of its second differentials is 0. Okay. So the idea is to figure out, for this idea about that being about the velocity and the acceleration, and the other idea being about the stopping distance, for this anti-operator in the differential, that to figure out this addition or power taking formula so that it works up that then you can figure out what makes it so for the formula that what is, according to these orders, able to A, either reduce the order, or B, build out a symmetry, or C, build out what would be a formula to make that reciprocating. These are the kinds of things that get into some ways to then be able to apply that maybe to a general higher order case, for example, or even just to solve some simple closed form things in the circle and the square. These kinds of things. So the Legendre equation, which is on these orders of these terms, and if there's, for example, it has some other things that make it so contrived about the arithmetic and algebraic things that work out its solutions. Has the finite regular singularities x equals plus minus 1. And so this kind of came up before. It's like, well, what does this singularity mean in the identity dimension? Well, it depends if you're writing it in the identity dimension or projecting it to the identity dimension, it would seem. I'm making this up as I go along because everything demands definition. Then it would be whether the regular singular point is 0 or 1, or 0 and root 2, or 0 and 2 root 2. And these kinds of things. But here it was about talking back to the analysis of that with respect to the linear fractional equation about the regular points at 0 and 1. Because basically, if you consider that as about an inflection, about terms like the higher powers of x, it's below the line, where the line here is x equals y. It's below the line from 0 to 1, and then it's above the line afterwards. And similarly with the higher order powers of the roots, it's above the line to there, and then it goes lower. And so these are the kinds of things established whether that's so for 0 and 1, where things to do in the logarithmic, like, oh, it's between 0 and e, or and so on, or the base of the logarithm. In order to study the solutions valid near x equals 1, it is advantageous to make the change of variable. Here the idea of this change of variable is change of coordinates, change of variables, ... It is advantageous to make the change of variable x equals 1 minus 2 epsilon, which transforms the equation into this it has the second order term that it has in the front is 1 minus x squared, so it just makes epsilon 1 minus epsilon. As noted before, that has a maximum if you consider only between 0 and 1 at 1/2, and it has a minimum everywhere else, or it's less on either side. So it has a central tendency, and it has an arithmetic and geometric and harmonic mean of a sort. This is the particular case of the hypergeometric equation. And so this is then when we got into the hypergeometric series, and I was reading about it a bit more, and then we got into there was discussion about the series, and there's kinds of two forms of series. And one is about powers and orthogonal functions, whose product is 0. And then these powers in multiplicative powers that, so orders, say, or ranks, that these orders and these powers then are just, they have an increasing denominator. That here is in terms of 2 to the n, or n bang. N factorial. That these are two kinds of series that mathematics is so far kind of built, that are these infinite series. There's one that's kind of categorized as sum of orthogonal terms in their powers, and there's other ones that's defined in terms of it's a power series and it's divided by a thing, or it's a power series and the numbers are between 0 and 1. So for a real power series, it's defined on all the positive numbers, or the positive and the negative numbers variously. They're usually defined on the reals or the complex numbers, the way these formulas for these series are written out, because it's easier to determine what are some roots in these sometimes, and some other ways to make up what they are in terms of the sinusoidal functions that otherwise go between -1 and 1, right? that there are these power series then that are between 0 and 1, so that the higher powers just naturally go to 0, and then whether the limit exists and they have a finite value and dot dot dot. And there are these ones that are divided as they go along, that the coefficient always includes an increasing term in terms of the exponential or the factorial, a value that grows larger than the power series term does in the powers of it, because n bang is bigger than n squared, and 2 to the n is bigger than n squared. And then there was discussion about how this ends up in the hypergeometric series for Legendre. It only uses some of the middle terms, or it basically skips a bunch of the first terms, and then where it starts from, then it spins off and is the rest of that series. Thus, the Legendre polynomial is even or odd according to its degree, n is even or odd. And then since Pn1 equals 1, we conclude that Pn-1 equals -1 to the n. That being a usual multiplicative constant you'll find in all sorts of solutions of differential equations with regards to the function being even or odd, because -1 to the n reflects that usually in the power formula that the functions are called even or odd because even functions have that f of -1 equals f1, or rather f of -1 equals negative f1, whereas odd functions have that f of -1 equals negative f1. Excuse me, I reversed that, but the point I hope will be clear. An important formula for Pnx, the Legendre polynomial, may be deduced from this last expansion. We observe that 2n minus 2r factorial over n minus 2r factorial times x to the n minus 2r equals dn over dx to the n, so that nth derivative in x times x to the 2n minus 2r. So this is a sort of formula, and it trades this multiplicative coefficient in the factorial to a differentiating constant, differentiating application of the differential operator to the same order on the other side, and that then it relates the powers of those two terms, kind of like as you would have an addition formula that x squared plus, or rather x squared times x squared is x to the 2 plus 2, and xm to the xl equals x to the, or rather xm times xl to the l equals x to the m plus l, these kinds of things. It's an addition formula that this has got a relation in these, this way algebraically, that's what defines the Legendre polynomials. And therefore the nth Legendre polynomial for the variable x is the nth derivative with respect to x of the sum of -1 to the r and x times x to the 2n minus 2r over this entire quantity 2 to the n r factorial n minus r factorial, and where r ranges originally from 0 to n. This is rather remarkable, and to see these things related in this way, but it's possible to find these things that make for factorial and exponential identities. And this is another thing I've found in terms of the square Cantor space. It's a thing. We may extend the range of summation, however, from r equals 0 to r equals n for the new terms of the sum are of degree less than n, and their nth derivatives vanish. Thus, we can employ the binomial theorem and obtain the Rodrigues formula. This is that the nth Legendre polynomial is 1 over 2 to the n, or the exponential to the n, dot n factorial times the quantity, the nth derivative with respect to x of this quantity x squared minus 1 to the n. We may prove from this formula that p sub n to the x has n distinct zeros between -1 and 1. That f naught equals x squared minus 1 to the n, fm equals f prime m minus 1 for m equals 1, 2, dot, 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 n, so that f sub n equals 2 to the n prime, or n factorial, Legendre, n of x. Then we prove by induction that f sub m has at least m distinct zeros in -1, 1. For this is true of f naught. Further, f m minus 1 has zeros at -1 and 1, and so if it has at least m minus 1 distinct zeros in -1 and 1, then by Rolle's theorem, f sub m has at least m distinct zeros there. The induction now proceeds. And then he gets into an argument after the Legendre polynomials in the Legendre equation for large values of x. So something like Stirling's approximation for x, or Hadamard's approximation for n factorial, make it so that there are certain functions that are unable to compute some closed forms for otherwise big things. Kind of like the old sum the numbers from 1 to 100. Well, how about just take 51 and multiply it by 50? That's a closed form, and it's making use of the fact that there's a symmetry, kind of like this between this, when n ranges from 0 to r, when you have r factorial times n minus r factorial, as it builds up, you can see that it's either side of that cascading into the middle. And so by adding up those terms, they multiply together and fulfill their counting arguments, everything being kind of a counting argument. That a counting argument says that by counting this and counting that, the tallies come up and it balances out, and all that. Finally, just the bits of sand, or the NAND gates that represent the machine integers on the chip. So these are the kinds of things then that get into closed forms for the large numbers. There's one thing that's greater. I mean, the larger number you can compute that is algebraic related to other numbers by the smallest formula is the best closed form, because you can compute the most amount of work that otherwise you'd have to do by the long way. For the least amount of work. So chapter 56 in this book is talking about something like this. And these days we call this approximation theory, and that every numerical method can, for example, find values it's used to solve these things. Call them solvers, and the whole idea is that, yeah, by Newton, Raphson, or Runge-Kutta, or these various methods of divide and conquer, or binary search, or usually it's in binary by finding something in midpoint, testing it either way, and then moving to the midpoint of that, testing it either way, binary search. That these are means to generate approximatively and iteratively for as much precision as can be, as much time there is to work on it, to build out these things and get closer and closer. They're not closed forms. They don't offer these inductive leaps about the deductive analysis of the inductive impasse, and they may be wrong in that sense. But they do represent solvers. And so these approximations in the approximation theory basically have that a formula approximates another formula, and then it's usually just written with two tildes or two wavy lines for the equals bars, like I approximate this, compared to the usual equals bar, and then the usual triple equals bar is like on the order of, probably just because they didn't quite, minus was already taken or whatever. And so similarly, the double wavy bars is an approximation, and the triple of that is an approximation on the order of, say, this being usual notation. So anyways, any approximation has two terms. It has the value, and then it has what's called the error term. The error term is what's left over. So like a sub x equals this other closed form plus error term. Kind of like when we have these constants of integration in these methods of the integrals, taking the integrals, it's similar with this kind of thing in the approximation theory, there's always an error term. And finding bounds on those error terms is basically how close is this approximation. Like the rule of 72 is like, well, how long does it take to double this according to interest rate? It's like, use the rule of 72. It's pretty accurate. You know, its error term is bounded and small. And so then the idea for these other kinds of solutions for large values, when we get into linearizations and the submersions and immersions, and a lot of the approaches in the differential geometry are these. They're approximations. And they result making a lot of different kinds of solutions simple, but they discard information. So they're not for everybody. Physical problems not infrequently demand the solution of a linear differential equation for large positive or large negative values of the argument x. In such cases, we use the reciprocal transformation x equals 1 over epsilon. Oh, well, this is a different approach. This is just scaling it down from 1 to infinity to 0, 1, whereby the Legendre polynomials come in and that being 53.1, just to refresh here. Oh, well, it's 55.1, 53.1. The regular singular function. So this is in terms of, again, an equation in the form px of y double prime plus qxy prime plus rxy. So this is about the regular singular functions again. And this is what's going on about any one of these ones where it has that it's second order in y prime, and it's a function of the y's of x, that this reciprocal transformation of x equals 1 over epsilon, whereby that function, p of x y double prime plus q of x y prime plus r of x y equals 0, becomes p of epsilon to the negative 1, or 1 over epsilon, times the quantity epsilon to the fourth d squared y over d epsilon squared plus 2 epsilon cubed over dy d epsilon plus q e to the negative 1, so just q of x, times the quantity negative epsilon squared dy over d epsilon plus r e to the negative 1 times y equals 0, retaining its linear form. The point x equals infinity is said to be ordinary singular, according as epsilon equals 0 is an ordinary or singular point of this transformed equation. Now, you'd be hard-pressed to find, usually, in the mathematics of today, when they say that f infinity, because it's considered not a number. Here is that it's a member of these numbers, and that 1 over it is 0. So this idea of what the behavior is for something for infinity, that for behavior of 1 over that for infinity is the behavior of that for 0. And it's well defined because that's why it's so. If you look to the differential geometry, one of these things is like we're defining curves and there's no 0 and no infinity. Well, what's the point of that? You just limited a lot of stuff, and it's like, well, it makes everything linear and easier from then on out. Fine, that's great. Unfortunately, there are perfect circles in our mathematics, so it's not complete. It's fine, that is great, and it's sensible and fungible and tractable, and so on. But here, it just, harkening back to the earlier part of the conversation about the identity dimension and how to treat the point in infinity and this kind of thing, and some of these regular singular points where they're 0, 1, and infinity, and for these harmonic functions, it's similarly as like to so. To build up something for it, then in terms of these symmetry is like, how about can it be that one's above the line and the other's below the line, but they're symmetrical about it. One is about the side going to 0, and the other is the side going to infinity, so that then you just have to commute to one side and double it to take its integral. That is kind of one of these ideas of what the methods, the analysis of such a contrivance can offer. In such cases, we use the point x equals infinity is said to be ordinary or singular. Accordingly, as epsilon equals 0 is an ordinary or singular point of this transformed equation. So transformation by coordinates and transformation of variables and substitution of variables and these kinds of things are very regular. And then in the differential analysis, what ends up getting tricky is how do you treat the differential when you transform the coordinate or transform the variable? And they call it substitution usually. The Legendre equation, so transformed, becomes 1 minus epsilon to the negative squared. So this is now taking that general form as of having regular singular points about p, q, and r in x, and then y double prime and y prime and y equals all that equals 0. So then the Legendre equation has that 1 minus x squared, and then this minus 2x. So the determinant x is minus 2. And then plus this n times n plus 1 on the y term, that being like a constant. That being for the nth Legendre polynomial. That it's written as so, but then instead of for y double prime, it's written epsilon to the fourth, d squared y, d epsilon squared, plus 2 epsilon cubed, dy, d epsilon. And so on. It's just written in terms of the substitution variable. This says or, and then this was how it was written in terms of L. L sub epsilon y equals this epsilon cubed, epsilon squared minus 1. This was the sigma, term of sigma. Dot, 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 assuming, and he says, assuming that y equals the sum of the coefficients in R of epsilon sigma plus R, we find that it looks the same, except just replacing x with epsilon, provided that C1, C2 are so chosen that this recurrence relation holds instead of that one for x. Alpha plus sigma plus r minus 1 minus n plus 1 dot 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 sigma plus r plus n plus 2 product of the r plus 2th coefficient, r plus second, sigma plus r times sigma plus r plus 1, the rth coefficient. The equation is thus satisfied if sigma equals negative n or n plus 1. When sigma equals negative n, the solution is of the form. And it just uses the even coefficients and the even powers of epsilon inverted, or back into x. With this recurrence relation of what's written off, r plus 2 times 2n minus r minus 1 equal of the r plus second coefficient equals negative n minus r and minus r minus 1 of the rth coefficient. Reverting to the variable x, we have the first solution. And it's a term in an expanding product with factors in n, and n times n minus 1 times n minus 2 times n minus 3, or the falling factorial. Falling factorial is like, the factorial is n times dot 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 1, and the falling factorial is n times dot 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 n minus r, you know, and it stops there or something like that. And the rising factorial is kind of the opposite, and it's also called the Poch hammer, P-O-C-H-H-A-M-M-E-R. And then that the denominator term is in 2n minus 1 times 2n minus 3. And so when you think of that in terms of an object or an operation, that's a sort of product of the factorials again, and figuring out what that means in terms of that those build out enough combinations that fall down what these coefficients would be. And taking this one coefficient equals C naught equals 2n bang over 2n times n bang squared. When n is a positive integer, we identify the solution with the polynomial Pn of x, Legendre nth polynomial. And then he gets into more substitutions and contrivances. Sigma equals n plus 1 finds a solution with this recurrence relation contrived. Then we obtain the second solution, When n is a positive integer, this series does not terminate. But since the recurrence relation exists and has a ratio between a term and its second next term, that limit goes to 1, it converges. And then taking the first coefficient, as was mentioned, except with n plus 2n plus 1 factorial instead of n plus 1, we obtain the second solution, and then it solves for q and x. So in terms of p and q and r, then it's solved for q, which is known as the Legendre function of the second kind. It is of opposite parity to the Legendre polynomial of the nth order. Note, the method explained in 38 enables us to determine a second solution by quadrature. So in 38, which was after problems involving curvature, in linear equations in the form of the general integral, there's reduction in the order, depression of the order. I'll read that briefly here in a minute. Substituting in y equals Pn of x, integral of v dx, we find for v the differential equation, from which, thus we have a second solution of a Legendre's equation in the form Legendre nth times the integral of in dx of 1 over this quantity, 1 minus x squared times the nth Legendre polynomial of x squared. So that's kind of interesting, that it becomes part of the recurrence relations. And so Legendre is found according to 2n and factorial and a couple of different things, these recurrence relations that make up for these neat kinds of things that make for reducing the order, then make for giving it an integral, for solving it via the quadrature. It is possible to prove that this is equal to q sub nx, provided that the lower limit of integration is taken at infinity. So these are the kinds of things. And then the next section gets into the Bessel function. So when you hear Bessel function and find J, so Legendre is polynomials, and they're called P, capital P. And the Bessel is polynomials, and they're called J. And there's first and second kinds. There's various kinds of these. And it starts talking about Frobenius and such. So I'll be getting, as I become more familiar with this book, I'm going to be becoming a little bit more familiar with this little book, because that's the end of the book then, and it's got a lot going on. So back in linear equations on page 81, we skipped about 50 pages looking from the first mention of singular points to the next. Depression of the order. When any integral of a reduced equation of order n is known, the equation can be transformed into another, also linear and reduced, of order n minus 1. So when you hear about like row echelon reduction or Gaussian elimination and a lot of these different things that make that if you have a given system of linear equations, you can line it up in a matrix and apply echelon reduction or rank echelon reduction or Gaussian elimination to these, then you can end up basically using arithmetic to transform these systems of linear equations by transforming their rows in this matrix. And so what results is you end up finding a sort of means to compute whether it has closed form or to deal with the less reducing the order. If the known integral is u sub 1, the transformation is u equals u sub 1 integral v dx, where v is a new dependent variable. This transformation and the proof are general, but for brevity we take an equation of the third order. P sub 0 u to the m plus p sub 1 u to the that's u triple prime. So coefficients in P, 0, 1, 2, 3, and then in derivatives in u triple prime, u double prime, u prime equals 0. So the sum of, and I would just kind of reverse those constants, because I want the indices of these constants now to be the same as the order of the term they represent. So usually you write the indices of these constants in the same order as you write the terms. And so usually in a power series, those are increasing in order. But here in these differential equations, sometimes they write it so they write the higher terms first. Just like you'd be familiar writing a polynomial as the higher order terms first. But here, the idea is to treat a sum, to be able to write this as the sum of the ith coefficient plus the ith derivative equals 0. The sum of those, that's be able to just, it's a convention of a notation, as otherwise not to have to write something like for I equals 1 to 4, the 4 minus ith coefficient times the ith derivative equals 0. ... where the coefficients are functions of x or constants. And similarly, if it, just like when the Legendre equation happens to have the functions in x of the same orders and the powers as these terms that are going to have the derivatives taken, keep them the same. So that if you can figure out a power taking formula for them, then you can cross those and reduce the order and compute closed forms. Substituting u equals u sub 1 integral v dx and u prime equals u1 prime integral v dx plus u1 v. So taking the products out in terms of computing into these things, they're expansions in terms of the substitution of variables. U double prime equals u sub 1 double prime integral v dx plus 2u prime v plus u v prime, and then u triple prime equals u sub 1 triple prime integral v dx plus 3u adding up the binomial coefficients. Let's kind of carry those out in terms of these functions that are linear, as was said. When any integral of a reduced equation, so it was linear and it was reduced of order n, and also linear and reduced. In rearranging, we have, it just brings together the terms of like things in terms of integral v dx and v prime and v double prime equals 0. Since u sub 1 is an integral, the first term disappears, leaving a reduced linear equation of the second order in v. And here we get a particular example. A particular integral is e to the x. Writing y equals e to the x integral v dx, y prime equals e to the x times the quantity integral v dx plus v, and y double prime equals e to the x integral v dx plus 2v plus v prime. We obtain an equation which reduces to xv prime minus v equals 0, giving v equals to ax, and the integral v dx equals ax squared plus b, and y equals e to the x times this quantity, ax squared plus b. A term, ax squared and plus b is a term, the second order in x, but it's got no first order term in it. But it does have a constant associated with it. Well, anyways, that's what I got into today, was a little bit more familiarity with Legendre and Bessel and Rodrigues' formula, and that's Rodrigues, Rodrigues' formula. And then there's also been these ideas that are kind of developing about the identity dimension and about the coordinate space and the coordinate settings, because there's two. There's one coordinate setting that's in the identity dimension, and there's one coordinate space that's kind of to the identity dimension. See? And so that is kind of an interesting thing. And maybe we'll have some tractability results. And what I need to do is find where most likely someone has spent years and years and years writing out just such a thing. And so it's always key to find such things, and if they're going to be considered as part of a development, because then, for example, they might help establish the desideratum requirements, or that the work is done by somebody in the library already, just leaving it for some historian in the library to do the work to find these things, vis-a-vis kind of just making them from whole cloth. And at the same time, trying to figure out, especially in the higher level, how to keep things all formal and rigorous and well-defined is not so easy, and it can be simpler sometimes in the smaller. The problem is just being absent some of the other usual higher level functions and fundamental theorems that make things so easy up and above. But when it's possible to figure out how to make these things so that then they bridge and bridge up to these higher level things, then it's possible to make smaller models that work up and compute all sorts of things in much more limited and restricted terms that still have the same effect and values in these bigger spaces because they're linear, or the identity dimension. It's kind of like considering that there's a field, and what does a field look like? Well, it's this sequence of all zeros and ones, or the square Cantor space. Well, what's its diagonal? Well, its diagonal looks like 0.0000, but its antidiagonal is 0.1111, and it's at the end of the list, because if you reverse the list, it would be opposite that. Well, all right, well, what's the point? Well, the point is, according to that, in the identity dimension in this square space, A is that the limit, as it were, exists. Rather, the point at infinity exists, but it's just the opposite what you start with. But B, it's that there's that this line drawing basically has length. You can think of it as having length root 2, which is 1.414, or greater than 1, or of length 1. Whether or not it is the metric in these coordinate settings. There's a coordinate setting where the length in the identity dimension is 1.0, and there's one where it's root 2. Well, all right then. Hey, have a great day. If you would. It's not all cultures appreciate being told that I wish it may it be so, God willing, or this, that you have a day that as far as days go, that it's good, have a good day. But it's not unusual for most people. Warm wishes. Good luck.